So the topic today is conservation of mechanical energy. That's what the topic in this video. The next one is going to be different. Now, what's a mechanical energy? It is the sum of potential and kinetic energies. If you add these two, that's what the mechanical energy. So the way we write that, E for mechanical energy is equal to U, which is the potential, plus K, which is the kinetic energy. Now, the topic is conservation of mechanical energy. What that means is the total amount, or the sum, if you add all the energy, mechanical energy, should be the same at any given point. As long as what? As long we have none, as long as we only have conservative forces. What's a conservative force? Like gravity. If you have non-conservative forces, then the sum will not be the same. So the sum is the same only if you have conservative forces. And gravity is conservative forces. If I add friction, which is non-conservative forces, the sum will not be the same. And you will see that later. So now, before we used to say, well, mechanical energy is, or energy is the change in kinetic energy. Now we're going to be dealing with both. So basically what we're telling you that if you take the final potential energy, the kinetic potential energy, and you add them, that should equal, that's again U and not a mu, it looks like a mu, the initial potential energy, let's see if I can rewrite that, plus the kinetic energy. Now, if you remember from last two sections, potential energy is what? Mass times gravity times height, that's the final height. And the kinetic energy is what? 1/2 the mass times final velocity squared. Should equal the initial potential energy, mass times gravity times height initial, plus the kinetic energy, initial kinetic energy is 1/2 mass V initial squared. That's the equation I'm going to be using for both. That sum has to stay the same. That was the experiment we did in the lab last class. Now, let's take an example. I'm going to take a roller coaster here. Six Flag, here we go. We'll use Six Flag. Let's say the height is 60 meters here. 60 meters. And you sitting up there in that cart there's you. And normally when you're at the top, you're barely moving. Let's say we'll give you initial velocity. I'll give you some numbers. If I give you 0, that means you're not moving. You're stuck there. Maybe you weren't moving, a gust of wind came in, pushed you at low speed. But I'll give you some initial velocity. Your initial velocity is 1 meter per second, barely moving. What is your velocity as you go over this bump here, which is 10 meters high? And what's your velocity when you level down here? So when you're down here, what's the velocity equal to when the height is 0? Now the one thing I'm going to assume here, there's no friction. If there is no friction, the only force acting you that making you go down is what? Gravity. Gravity is a conservative force. When you have a conservative force, we have conservation of energy. That means if I calculate, we'll call this point the top A. I'll call this point B here, and I'll call this point C here. If I calculate the potential and the kinetic at A, it should equal the potential and the kinetic at B when you add them. It should equal the potential and the kinetic at C when you add them. The sum should be the same. Yep, that's the lab. So at A, this is at B here. We'll look at that. And this is at C. Let's look at A. Now, I never gave you the mass. Yes?
So that only works only without friction.
If there's no friction. Yeah, if you have friction, that's non-conservative. That's the next section, the next video. So now, what's my potential energy? I keep saying PE for potential. That's what I usually write, but our book uses U. It's mass times gravity times height. What was my mass here? M, unknown. What's gravity? 9.8. What's the height? 60. So you do the math. It is 588 m. Because I don't know what the mass is, so I can't really give you a number. And I don't want to give you a mass. I'm trying to prove to you, when you're on that roller coaster, it doesn't matter if the person is really a child or a 600-pound person. It does not change your speed. People think, oh, because you're heavier, your speed is going to be much faster. No, it doesn't make a difference.
Why'd you convert it to 60?
To what?
No, the height was 60.
Height was 60.
Oh, the height, okay.
Yeah. The kinetic energy, it's 1/2 the mass times the velocity squared. So 1/2 m, the velocity is 1 squared, that's 0.5 m. And what's the total energy there? E, which is the potential energy, plus the kinetic energy, that should equal to what? 588.5 m. That's a point A. Let's look at point B. What's my potential energy? Mass, gravity, height. M, 9.8 times 10, that's 98 m. What's my kinetic energy? 1/2 mass times velocity squared. Oh, I don't know what the velocity. So that's all I know. So what's my total energy? So the total mechanical energy is going to be what? 98 m plus 1/2 m v squared. Now let's take point C, then we'll start looking back and see. Potential energy is what? Mass, gravity, height. My height is 0. That's 0. My kinetic energy is 1/2 the mass times the velocity at C. I should call the velocity at B here so I'll know which velocity I'm talking about. You know? So what's my total mechanical energy? Which is the sum of them. That's 1/2 mass velocity as c squared. What do we know about these two numbers? They should be the same. Just like these two should be the same. These two should be the same. They have to equal to each other. So let's set them equal to each other. This is the total at A. This is at B. This is at C. So the total mechanical energy at A should equal the total mechanical energy at B. 588.5 M equals 98 M plus 1/2 M velocity at B squared. And what do you notice? There's M in every one of them, right? Mathematically, you can divide every term by M, and that does not change your answer. So you end up with 588.5 equals 98 plus 1/2 the velocity at B squared. What do we do now? Subtract 98 from each side. $588.5 minus the 98. 490.5 equals 1/2 the velocity at B squared. Multiply both sides by 2 to get rid of the 1/2. 981. And the velocity at B will be what? The square root of that number. 31.3.
Yeah.
That's how fast you'll be going on that ride when you hit that point. 31.3 meters per second times 2.24, just to give you an idea, 70 miles an hour. Now, if you think that's fast, how fast will you go when you hit point C right before they apply the brakes? Right there. Remember, the sum at any given point is the same. The sum at A and the sum at C are the same. Anywhere on that track, the sum is the same. Doesn't matter what point you pick. What is the sum at A? 588.5. And the sum at C is what? 1/2 MVC squared. And the m's will cancel each other out if you divide by m on both sides. Two times that number. 1177. VC is the square root of 1177. .3 meters per second. Again, times 2.24. Now you're going 77 miles an hour. Notice the height's only 60 meters. Imagine if we make the height now 100 meters. Imagine if we give you initial velocity on the top instead of 1 meter per second. Some of the ride actually, they jolt you with that initial velocity. 15, 20 miles per hour to start with. You do 15, 20 miles per hour, your velocity is now 100, 120, 130 miles per hour down here. Then you gotta stop. And these brakes better work. Otherwise, we got a problem. Now again, we can use conservation of energy in all the problems. If you remember earlier, we did projectile. We did somebody jumping from a diving board. How fast before they hit the water? Remember that? We did some problems like this. Somebody standing on a diving board. There's the water. Let's say this is a 10-meter diving board. And steps off the diving board, that means the initial velocity is 0. You can jump upward if you want to, like a diver, or hit the diving board and go up. And see, you know what? Let's do that instead of just standing. Let's give them initial velocity. Anyone dives? Any divers in this room? When you hit that diving board and you bounce up, how fast are you moving? What's the velocity?
Just pick a number.
5 meters per second.
Maybe. I'm little though. So
Going upward. So you jump up there, you hit the diving board, you go up, spring up there at 5 meters per second, you go to the top and you come down, there's your legs, there's your arms, and there's your head. You're diving into the water.
The hand should be.
The hand, yeah, should be forward, but this one is not a good diver. What's the found velocity?
You look like they're gonna die.
They're gonna break the way, no, I shouldn't say that, on video especially. So they're trying to kill themselves, but...
Yeah, I dove for the high school.
So can we calculate? Now we can use the old physics that we learned.
Oh, God.
We know the initial velocity is 5 meters per second. Upward is plus. We know the initial height is 10 meters. What was the final height right before they hit the water?
0.
0. What's the acceleration? Negative 9.8, yes. And we're looking for the final velocity. Is there an equation that ties all these pieces together? I think we had one before. It says V final squared equals V initial squared plus 2A, or G if you want to use G here, times the change in Y. We just use X's when we did them before because you were going the X direction. Today you're going in the Y direction. Times Y, which is what? 0 minus 10 this is 25. 196 plus, that's 2 negative, we'll make it a plus. V squared equals 221. What's V? The square root of 221. 14.86 or 14.9 meters per second. So you're hitting the water 33 miles per hour. We were talking about last time, Valentino, you said, that's really like I said, when you hit the water, it says it hurts. You're hitting the water 33 miles per hour. So if you don't break that fall, if you don't open that water to go through it, if you just hit it flat on your back,
You're dead.
that's not going to be a pleasant dive there.
So when you fall, like that's why people die falling off a bridge into water. It's
Yeah.
because if they're high enough up, it's like hitting concrete.
Exactly. You got to push that water quickly to sink
The
in.
surface tension.
Yep. So now if you actually, unless you make your body like a pencil, stick your toes forward, if you land on your
What if you
feet,
dropped a rock first? And then
well, good luck.
You could hit that rock.
Or have a friend push your friend down before you, let them open that water for you. Eventually, what happens, if you think of that, as your friend opens the water, it's going to close back in. By the time you get to you, you're done. Yeah. So now,
You get an A if you survive.
yeah. So can we do this? The problem here Not using this equation, conservation of energy. If we with this, we neglect friction, obviously. If we neglect friction, the only force we have acting on us is what? Gravity. So we have conservation of energy. I'll call the top, well, if I calculate the potential energy at the top and the kinetic energy at the top and add them, so if I get the total mechanical energy at the top should equal the total mechanical energy at the bottom. B for bottom, I'll write BOT and TOP. How is that? Top and bottom. It should be the same. So on the top we have potential energy and we have kinetic energy on the top. The bottom we have what? We'll say potential energy. We'll see what that value is. Plus kinetic energy at the bottom. By the way, this value here, mathematically you really should write minus or indicate it's going which way? Down, because the minus tells you the direction. When you have something squared equals a number, it could be plus or minus. So if that was like a homework problem or a test question, you want to write minus or indicate down one way or another. But let's look at the top. What do we have for potential energy? Mass, I never gave you the mass. Gravity, 9.8. The height is 10. Plus the kinetic energy, which is 1/2 the mass times the velocity squared. The bottom, mass times gravity, 9.8, and what's the height? 0. Plus the kinetic energy, which is 1/2 mass, the velocity squared. And notice every term has m in it, so if you divide by m, the m's will disappear. So what do we have? 98 plus 25 divided by 2 is what? 12.5 equals 0 plus 1/2 v squared. 110.5 equals v squared. 1/2 v squared. V squared equals what? 221. Look at that number. Look right here. What was v squared equal to? 221. V squared here is what? 221, the same number. So what's v? It's going to be 14.9 meters per second. Again, down. If you want to write that as without the down sign, you can say negative 14.9 meters per second. Again, the minus sign indicates it's down. You can either put the minus sign to indicate it's down, or sometimes in our book, they'll say the magnitude is 14.9. They'll give you the direction you're supposed to click on, down or up. But it's the same answer. A lot of these problems you can do this way. Let's do a projectile problem and show you how to do it both ways. Let's take one. So let's do baseball. A player of the Red Sox, Mookie Betts. Here we go. Yep. If you're a Yankee fan, you can use Aaron Judge.
I like that you know that.
I know all of them. I love sports. So now we hit the ball. It's a home run. And somebody catches the ball right there in the stand. This is the wall here, if it's Fenway Park, the Green Monster. So you didn't catch the ball the same height. Somebody up there in the Green Monster caught the ball, or on the upper deck there. We know the mass of that baseball, by the way, is about 150 grams. So the mass of the baseball, it's 150 grams, which is roughly 0.15 kilogram. Well, exactly 0.15. Now the ball leaves the bat in this direction with initial speed of 36 meters per second. Notice which direction it's going. And the person caught the ball here. That person happens to be, I don't know, let's give you some height. It was 7.5 meters above where the ball left. The person was on the green monster up there, on the balcony. Neglect wind resistance, friction. So no friction, I'm telling you here. Can you tell me what was the speed here before the person caught that ball? How fast was it moving? Now, if I don't want to use energy here to do the problem, I can go back to I learned about, kind of review for the final exam here, about projectile. Let's see if I gave you a distance where the person caught the ball. Where is he standing? No, I didn't give you that distance. Okay. With the information I gave you, we might be a little bit here. We'll see if we have enough information to do it the old-fashioned way. I might left some stuff out, maybe, you know. In projectile, we used to break it X component and Y component. Remember that? Mm-hmm. I have a couple of problems here. I left a lot of stuff in this problem. What did I leave? The angle, yep. We don't know what that angle. Because the initial velocity in X direction is what? It used to be 36 cosine. I'm going to tell you, you will not be able to solve it this way with the information I gave you. Not enough information in it, unless I start giving you more. In the Y direction, what's the initial velocity in the Y direction? 36 sine of theta. That's an unknown. Theta is unknown. That's one unknown. In the X direction, there's only one equation. X equals the initial velocity in the X direction times the time. I don't know X. I don't know the time. I don't know theta. Three unknowns right there. I'm doomed. Three unknowns. Can't do it. So I have X equals 36 cosine theta times t. How many unknowns do you see there? 1, 2, 3. Three unknowns. I need three equations when you have three unknowns. Well, let's look at the Y direction. I know the initial height. If I use this as initial height, that's 0. I know the final height where the person caught the ball, which is 7.5. I know the acceleration, which is what?
36 meters per second.
Negative 9.8 meters per second squared, right? And I'm looking for the final velocity. I'm almost there. If I gave you one more, if I gave you theta, I could have done it, by the way. But I didn't give you theta in this example. I might go back and give you theta and show you what that number is. So now I have V final equals V initial squared plus 2A, the change in Y. Where's my V final? Unknown, we're looking for it. What's my V initial? 36 sine of theta. And you're going to square that. Plus 2 times negative 9.8 times Y, which is 7.5 minus 0. How many unknowns? 2 unknowns. So we have right now, we have 2 equations by how many unknowns? I have theta, t, x, and v. 4 unknowns. None of us. There's not a single person on this planet that can solve 2 equations by 4 unknowns, gives you a number for an answer. There's not a single person. As smart as they come, you can't. If you have 4 unknowns and you want to get a number for an answer, you better have 4 equations. If you have 3 unknowns, you better have 3 equations. If you have 2 unknowns, you better have 2 equations. So you really can't do the problem the way it is with the old method. I got to start giving you some stuff. I either got to give you where the person caught the ball, how far, and what was that angle. If I do that, I can finish it because now 2 of the unknowns will disappear. I'll have 2 equations by 2 unknowns. But I'm stubborn. I don't want to give you the other information. I go, nope, that's it. That's all you know. Because I can solve it with that information. So let's take another look at it. Let me redraw the picture. The mass is 0.15 kilogram. It leaves in this direction. Velocity equals 36. And I don't care about the angle. Somebody catches it up here. The velocity is unknown. And I know the height here. What did I use? 7.5 meters. This is A, that's B. Since neglect friction, it says no friction here. The only force acting on that ball is gravity. And gravity is a conservative force. I can use conservation of energy, mechanical energy. The mechanical energy at A should equal the mechanical energy at B. What's the mechanical energy? That's potential energy at A plus kinetic energy at A should equal potential energy at B plus kinetic energy at B. Let's look at my, if I use this as reference where the ball was hit, what is my initial height? 0. So mass, which is 0.15, gravity, which is 9.8, times the initial height, which is 0. That's your potential energy. Your kinetic energy, 1/2, mass, 0.15, times the velocity squared. Notice I don't have to break the velocity to x and y components. What is the potential energy here? Mass, gravity. What was my initial height? I mean final height, not the initial, sorry. Yep. 7.5 plus the kinetic energy, 1/2 mass times the velocity squared, which is unknown. Zero plus, let's see what that number is. 97.2. This is 11.025. .075, the velocity of b squared. Move this to the side and subtract it from this one. 97.2 minus 11.025. 86.175 equals .075 velocity at b squared. Divide that. It's 1149. What is the velocity at b is going to be? The square root of that number at 33.9 meters per second. So that ball is still cruising. Almost 34 meters per second. That's 70 miles an hour still moving. It's coming at you. You better use a glove there when you catch it. Your hand's gonna sting there. And you can do the same thing for water slide. When you're going down the water slide, the water really is supposed to simulate no friction. So you can find out how fast when you go in water slide when you hit that water. And doesn't make a difference. Like if the water slide, we'll do this example. If you have a water slide like at home, somebody does water slide that looks like this, steep, and the height here is 3 meters. This is the pool here. Or you do the water slide like this, long water slide. As long as the height here is 3 meters. Would that change your speed when you hit the water? What's your velocity right here, right before you hit the water? Let's see, you're holding on the railing here, on the edge of that water slide, so when moving there, then you let go. So your initial velocity here was 0. Same thing right here. You think it'll make a difference?
No.
You should hit them at the same speed. This one looks scary. It looks like, oh, you're coming down. Or you can make it straight down, jump in. Stand there. The thing breaks and you fall down. Straight down. You're still going to hit the water at the same speed. Because when you look at the top here, there is no kinetic energy at the top. Here at the top is going to be only potential energy. Mass, gravity 9.8 times the height, which is 3. $29.4 m. Your kinetic energy at the top is what? 1/2 mass times the velocity square. And that's a 0. So what is the total at the top? 29.4 times m. Let's look at the bottom. I'm still dealing with this side, so that picture we didn't touch yet. This picture. At the bottom. I was about to try them all as a sum, but that's the potential first. Then we'll add them. Let's do the potential energy at the top. I mean, we did the top, the bottom now, right?
Yeah.
That's the bottom. What do we have at the bottom? What's your potential energy? Isn't the height 0? Because I'm using that edge here as reference. Otherwise, I have to know what the height of that and use it for the potential here. What's my kinetic energy at the bottom? And what is the mechanical energy at the bottom? The sum of them. And what do we know about the sum on the top and the bottom? Isn't that the same? So if you set them equal to each other, and since the m shows up on both sides, we can cancel it. $29.4 times 2, 58.8. And what's the velocity when you hit the bottom? Is that the square root of 58.8, 7.7 meters per second. 7.7 meters per second.
Is it gonna be the same?
Should be the same.
Height?
Yep. Yep. So when we go right here, my potential energy, again, I'm using this one as reference here, where the edge of that pool. Not the pool, I mean where the person leaves that diving board. The pool is down here. So my potential energy at the top, it's mass, gravity, height, still going to be 29.4 m. Oh, this marker is dying too now. Okay. Kinetic energy at the top. One half mass, but your velocity is 0 at the top, which is 0. So what is the sum? 29.4 m. Bottom there, what's the potential energy at the bottom? Mass, gravity, my height is 0. That's a 0. What's my kinetic energy at the bottom? 1 half the mass times the velocity squared. And what's the sum? One half mv squared. What do we know about these two numbers, the top and the bottom? They should be the same. Let's set them equal to each other. And what do you notice? It's the same exact thing. V squared equals what? 58.8. And V equals 7.7 meters per second. So it doesn't matter if the diving board is steep or gradual. When you leave that diving board, the speed you're going to leave at, not diving board, water slide, the speed you're going to leave that water slide is 7.7 meters per second, regardless if it's like this or like that. Or even if you come straight down. If you step off the diving board here and you come straight down, you'll hit the water, or you reach this point at a speed of 7.7 meters per second. You can see that sometimes a skier will come in, same idea, and they're cruising, or skateboard people, and they have like initial speed, and they're trying to climb the hill, and they start to climb. If they don't push, a lot of times they don't make it to the top of the hill. Why? Because the kinetic energy they have is going to become all potential energy as you go up there. And it's not enough. That show that the ninja one.
Ninja Warrior.
Ninja Warrior, yep. To climb that wall. You see them, it's a flat wall, then you got to climb up there. They start running and they got to climb because you got to have that kinetic energy to compensate for that potential energy to climb it. When you're coming down that wall there, you're running this, the wall looks like this. It's almost straight up. When you're coming down here, all you have here is kinetic energy. And you try to make sure you have enough kinetic energy. If the height is 5 meters here, let's say it can't be 5 meters, they'll never make it. Let's say it's 3 meters. 10 feet?
Yeah.
3 meters then. Yeah, that's about 3 meters. You better make sure you have enough, or your shoe is going to have some friction to push you up, to continue pushing you up there to reach that top. Because right there, if you just come here and try to jump and grab the end, you have kinetic energy, which is 1/2 mv squared. And just to reach that height with zero velocity here, your potential energy alone, it's mass times gravity times height. So that velocity better be bigger than whatever that potential energy. If it's not, you're not making it to the top there. And again, you see it with the skiers. They come, like they'll be skiing, there'll be a little mountain like this. Well, not a mountain, but a little bump there. The skiers coming in, or skateboard, and they're moving, they try to climb that. If they have enough speed, they will climb it and continue to go. If they don't have enough speed, they get to this point, unless they're pushed back, or they're going to slide down. I don't need that sheet, so I won't put in the notes. While we're talking about this, let's bring in a spring here, because I keep thinking about the roller coaster and something going to stop me when I'm coming down the roller coaster at a speed of 78 miles per hour. Who's going to stop me down there? How are we going to stop you? And that's where the friction comes in. But we're not going to bring it yet. So we have actually here a block of wood. It's moving down on this horizontal surface, block of wood. 1.70 kilogram. It's moving in this direction. Assume no friction again. Now, was the block of wood coming from top there? We don't care about that. All we know, reach this point, it's a flat area, and it's moving in that direction. Now we have a spring here. It's attached there. So the block of wood is going to hit that spring. That's the wall here. It's going to compress it. First, let's talk about the spring here. What do we know about the spring? Spring has a constant. K equals, I don't know, 950 meters per second. So it's a good spring. Now, what will happen as the block hits this one? It's going to compress the spring, and it's going to stop. Let's say it compresses that as it hits it, so I'll draw another picture here. And there's the block. So it compressed the spring by how much? Let's say 4.6 meters. Centimeters, not meters. 4.6 meters. We've got a long spring there. Centimeter. What was the initial speed of this one? Again, we're neglecting friction.
Is that 4.6?
4.6 centimeters, yep. Let's see what happened here. Right before this one hits this, right before, when it's right here, didn't touch it yet. This movement, the velocity equals unknown. Let's look at the total energy now we have. This is the before. And this is the after. And they have to equal. We talked about springs last time. They store energy and release them. So that's conservation. So before this one touches that, right before, what was my potential? If I use the ground here, it was sliding on as level height 0. What was my potential energy? It's mass. So we have a potential energy. I'll put the numbers. The height is 0, correct. Which is the mass, 1.7. Gravity, 9.8. Times the height, which is 0. What was the kinetic energy then? 1/2 the mass, which is 1.7, times the velocity squared. What about the spring? What was the energy in the spring? 1/2 K, which is 950, times the distance squared, which is 0 squared. 1/2 K times X. That's the energy in the spring. The kinetic energy is 1/2 mv squared. The potential energy is mass times gravity times height. So that's what I'm using. The block comes in, pushes on the spring, collide, and they stop. So let's see the after. What's my potential energy? Mass, 1.70. Gravity, which is what? 9.8. And what's the height? Still 0. It's horizontal table. What about the kinetic energy? Is that block of wood still moving? No. Velocity is 0. What about the spring? 1/2 K, which is what? 950 times D squared. And what's D here? Change it to a meter. 0.046 squared. So I have 1/2 times 1.7. What's that? 0.85. V squared equals, that's 0, that's 0. Let's see what that number. 0.5 times 9.8 times 0.046 squared. Oh, I multiplied wrong. 0.5 times what? 950, I don't know why I said 9.8, 950 times 0.046 squared. I came up with 1.0051. Divide that by 0.85. It's the square root of that number. 1.087 meters per second. That's how fast the block was moving. 1.09 meters per second. So again, spring force is conservative force. You got to look at the before and the after when you have a story like that. How much energy was in that spring before, and how much energy was in that spring after? Well, how much is it compressed? Based on that, we can figure these numbers. And when you think about these guns, I'm going to talk about toy guns that we use with the spring in them, compress the spring. It really works on that principle, backward. So if I have, for example, one of those, I really shouldn't be throwing a gun here, but it's a toy gun. I told you I'm not an artist there. It has a spring in it. And you take actually that spring and you load it by pushing that arrow in it, whatever you're trying to fire there, you know. So the spring looks like this. Let's give it a value of K over 1,000. I'm just numbers here for the spring. You take your dart, push it through, and now what happens to that spring? That spring becomes compressed like this. And the dart is sitting right there. That's the dart. It's going to be firing there. It's going to stick to, I don't know. You compress that string. And now that spring being compressed by how much? It used to be, right, let's say 10 centimeters. That's a big, actually, toy gun. If you're compressing that by 10 centimeters, about this much. So when you fire it, what is the velocity of that when it leaves? It leaves actually when this one reaches that point. That's no longer touching it. The spring is back to its old natural length. So before that, since I'm holding the gun horizontally, that toy gun, there's no change in potential. My potential is gone, it's zero on both sides. So the potential plus the kinetic plus the spring equals the potential plus the kinetic plus the spring. If I'm using the height there as reference there, my potential is zero for both cases. I don't even have to waste time on it. My kinetic is zero initially. Why? Because this is compressed and it's not moving. That dart just sitting inside the gun. I pull the trigger, the darts start to move. Well, how much energy the spring had? That's 1/2 K, which is what? 1,000 times the distance, compressed distance squared. 1/2 kx squared. This is the before. The after, here's what's going to happen. There's the spring. Now it's back to natural length. And there's that dart coming out of it. My potential is zero. My kinetic is what? 1/2. I forgot to give you the mass for that dart. Even they're not that heavy, the darts. What is it, 5 grams? That's 0.005 times the velocity squared. What about the spring now? The spring is back to its natural position there. It's not compressed anymore.
Zero.
So as a zero. Notice mathematically I can scrap the 1/2 from both sides. Because the 1/2 shows up on both sides, I can just cancel them. I have it flying out now. This one will kill somebody probably, no. 10 divided by 0.005. 2,000. What's the velocity? The square root of 2,000. Yeah, it is coming fast. You better not shoot somebody in the face with it. 44 meters per second. I compressed it 10 centimeters. That's like this much. The spring constant's decent value too I gave you. It's not like the one you see in toys. If I made that number 100, that velocity will drop by a lot more. You know. So if I use a cheaper spring here, instead of 1,000, I put 100 here. This will be a 1, just to give you an idea. That will be 200. The square root of that will be 14. And that's more reasonable. Yeah, if 1,000 wasn't a good choice, maybe 100 would have been a better choice. So instead of 44 meters per second, it's going to 14 meters per second. You know, decent speed to make it to the wall and stick to the wall. But that's how these actually toys work on that principle. Conservation of energy.